We'll get started here. We'll talk about solar sails. There's a new solar sail mission that was just launched. And so we'll back up a little bit and talk about it. First of all, what is a solar sail? It is literally sailing through space based on the pressure you get from the sun. Photons have momentum, and they bounce into a surface like that reflector there, and they bounce back off. The idea is it comes in, you have the angle of incidence equals the angle of reflection and all that. So, it bounces off at an angle. So if the plate's at an angle, you can direct the thing different than just the direction the sunlight's coming from. Analogous to how you can tack with wind on the earth with a sailboat. So it's sort of analogous, not exactly the same mechanism. But anyway, the idea is by angling the thing compared to the direction the sunlight's coming from, you can orient yourself and you can change your direction. And this goes back to science fiction, but it is actually true. People have proposed that also you could power a solar sail with lasers from a distance. Then that way you get a lot more concentrated light. It'll spread out a little bit, even at a long distance, or maybe quite a bit, but that's okay. You just make the reflector as big as you need to be able to catch that. So that's the basic idea. There have been built already. Actually, the most successful one was the very first one that was done outside of Earth. The Japanese did one back in 2010, and that's actually, it's a drawing of it there. And what's common to most of the solar sail projects is the main spacecraft body is something fairly small in the center of it. And then typically you have booms, just like you have booms on a sailboat. They're just basically masts on which you string up this big sail, and there's a sail there. Those two key parts are in all these things. Why do you want solar sails? Well, the big thing is the solar sail mechanism uses no propellant. Now, to get the thing going the right way or to make really big course changes, you may want to have some propellant. And they've gone either way on this. The other thing is there's very few moving parts in this thing to fail once the sail is opened up. In theory, you can get to very high speed with this. It takes a long time to do it. So you're not going to send people, on solar sails. It seems like that's pretty unlikely. But you might send cargo. What you're really going to use it for is mostly missions of exploration. You might want to survey asteroids. And actually, one of the ones that failed more recently was, in fact, going to be an asteroid surveying one, which we'll talk about.
There was a question about material for the solar sail and damage from micrometeorites.
It's actually extremely thin, typically a polymer. It's like mylar. If you saw like mylar balloons or something, very, very thin, and they can get punctured. And usually their design accounts for some of that. It doesn't necessarily invalidate it. Unlike a balloon, it's not just going to deflate or something. You just have little holes that won't be quite as effective because you're still going to get light reflecting off the rest of it. So even if it gets some little holes in it, it's not the end. Now, if it gets all scoured by a lot of micrometeorites, maybe the reflection won't be so good. So it will affect it, but it won't necessarily destroy it. That picture, that's back in 2010. More details on this. That was 46 feet by 46 feet, gives you an idea. It's a polymer, 7.5 micrometers thick, so very, very thin. If you compare that to your garbage bags, those are measured in millimeters. You're talking about units that are 1/1000th the size of that. That gives you an idea. Because you basically want as little weight as possible, the solar pressure is not very much. So you want everything to be light, and that's why they keep making them thinner and thinner. The thing weighed 310 kilograms. It was reflective. There is possibly another way of doing solar sails relying on diffraction, which is a different thing, which is interference of light waves. It's a much more complicated thing to do. It's been proposed.
And studies of it are being funded by NASA through their NIAC program. That NIAC acronym stands for NASA Innovative Advanced Concepts. Every year they do a public review of all the research they fund. Last year Doug attended in person and I attended it remotely. The studies are quite interesting. Anyway, getting back to solar cells based on diffraction.
With diffraction, you can essentially direct the reflected light almost anywhere you want. And so you have much better control over it. So there's some benefits to it. Also, a lot of it just passes through and it doesn't heat the thing up as much. A couple things about this one. They need electrical power. So they put some solar cells, kind of that band around there that's shown in this diagram. But there's something else they did that was very interesting that nobody's done since. If you want to change your direction, you got to change the angle at which the sun hits it. Well, how do you do that? You don't want to use propellant to do that. That's no good. That kind of defeats the whole idea of not needing it. So what the Japanese came up with was what you want to look at is the difference between the center of mass and the center of the pressure exerted by the sun. If you can shift that around, you can control the direction. And what they did was around the outside edge there, they put some LCD panels or crystals, and they just basically could cut it off so it reflected or didn't reflect. So what you do is maybe on one half there, you would cut back on the reflections quite a bit, and that would cause the whole thing to tip. And it's kind of interesting. The amazing thing is it worked. This was on a mission where they had something else going on. They tagged along on a mission to Venus. And so the whole thing kind of started closer to Venus. But anyway, around 2013, they had increased their speed. Now, it only increased it by 890 miles an hour, which doesn't sound like a lot, but still it does show that the mechanism was working. They lost contact around 2015, and it was maybe 110 million kilometers from Earth. And somewhere in solar orbit, somewhere going away from Venus. So it's out there. It does work. That part's been proved. Now, next step, NASA did a project called the Near Earth Asteroid Scout. They were going to go out and look at small asteroids, essentially doing surveying and scan them. Now, this looks like some kind of weird ice cream cone. It's not. Those little red rays there are supposed to indicate the scanning is going on. This is an artist's conception kind of a thing. It doesn't really look like an ice cream cone. That's an asteroid, and that's the thing going by it. The craft itself is, of course, the solar sail there, and then there's a little CubeSat down inside of it, meaning pretty small. That thing is 30 by 30 feet. It was a little bit smaller. You think of it like, like a tennis court kind of size. They used thin metal booms. They shielded them from the sun. What they concluded, and actually their biggest concern, was that when those metal booms get heated up, they warp. And that screws up the direction they're pointing. So that was the biggest concern. They essentially always hid that, made sure that the sun was on the other side. That was a big deal in their design. So the satellite in the center is a 6-unit CubeSat. Each unit is a 4-inch cube. And so it's like a shoebox size. So that thing in the center is sort of shoebox size. The whole thing weighed about 31 pounds. And notice they got the thickness of the solar sail down to 2.5 micrometers. The last one was 7 something. They're definitely going for even lighter. And what they do is they put a thin layer of aluminum on it to help the reflection. This actually included conventional control mechanisms. It had reaction wheels. These are basically spinning flywheels driven by a motor. So if you want to rotate the craft, you just either speed up the motor or slow it down, and you transfer momentum between that spinning wheel. And that's what's done actually in every satellite, typically. Then they had cold gas thrusters for major moves. If they wanted to make a big, big change, something you can't do with a solar sail because the pressure is so little. They still had some of that. But they went a little further. They have another new thing called the active mass translator, and that's in the center of it. And what they did was they went back to the Japanese idea, and they said, well, okay, shift the center of mass. We have a weight, we're just going to move it, either to left, right, or up and down, to shift the center of mass of the whole thing. And so they made that work, or they're going to make that work. The catch is the whole thing died. It was part of the Artemis 1 mission. Remember the Artemis 1 mission? That was to send an unmanned craft around the moon. It was the first of the Artemis missions. But they had a bunch of ride shares, secondary missions. There were 10 of them. Unfortunately, that one had gotten delayed so much that most of the batteries gave out on a lot of the things that were in that. And this apparently was one of those, because this failed. It lost contact immediately after being launched. And what most people think happened was probably the battery was just dead. And that was just from sitting around too long. It was too bad. But that, these things happen. Okay, so the one that just launched, it's a new one, a little different. They made a little different polymer. We're down to 2 micrometers now. This one has foldable metal booms also. They coat it with aluminum. It's 0.1 nanometers. And again, we're talking yet another factor of 1,000 on thickness. You're talking down to a few atoms thick probably. And the other side's coated with chrome for heat radiation. This one, the CubeSat, they call that a microwave size, 12-unit CubeSat, 9 by 9 by 13 inches. They're just doing this in low Earth orbit right now. They want to test the unfolding mechanism, because what they're trying to do is figure out how you pack something into such a small package and merely make sure you can get it undone. Not an easy thing. They're going to consider this mission a success if they just manage to get the sails extended. And that just got launched on an Electron rocket. So it's kind of funny. Their previous launch that NASA had for a solar sail was on the biggest rocket that was available at the time, which is SLS. This one is launched on probably the smallest commercial one. And it was shared with another payload as well. This whole thing is just not that big. There's a video of this showing the sails opening here. And they don't show it going all the way because it'll suddenly flip. You'll see the, what it looks like there. So, but anyway, this is why they want to test it out. It's, a lot of things could go wrong. Things could break, get holes, whatever. It's delicate. This is what it looks like, by the way. This is that solar sail. You can see the size based on the people there. That's what it looks like when it's fully extended. I think that's probably it.
Other space-related videos or slide presentations by me are available at the link shown here. That includes a list of videos at my YouTube channel, so you can view them or subscribe for notifications about future videos. These presentations are mostly made as part of the meetings of National Space Society's North Houston chapter, and a link to that is shown. Topics like these are presented as part of a monthly news segment, and there are also lots of other interesting speakers and open discussions. You can attend in person or online via Zoom. Come join us.